All right. So today we're going to talk about coordinate covalent bonds. It's a bit of a mini lesson off of covalent bonds. And so what happens is that sometimes things aren't ideal. And so we're going to ask ourselves, what is a covalent bond? And we're going to get at that covalent bond is the sharing of two electrons. And so, well, where do the two have to come from? And the answer is one of the atoms, maybe both of the atoms, but it doesn't really matter as long as they're being shared where they come from. They could be each one donates one. That's a very normal way, but it doesn't have to be that way. And so we're going to take a quick look at carbon monoxide. Now, with carbon monoxide, we know it exists. It is indeed a gas that exists. So, if we take a look at carbon and oxygen and we draw their normal Lewis dot structure, we're going to get a problem when we try to bond them, right? Because we make one bond here and we make one bond here. And now oxygen is done. But carbon's not. Carbon still has these two electrons. And that's the problem. It's unstable. Now in carbon dioxide, another oxygen comes in on this side, but this is not carbon dioxide. This is carbon monoxide. And so what's going to happen here is that it's going to bond in a bit of an unideal fashion, but it happens. Okay? Well, initially we were saying that any side with one electron is a bonding site, and any side with two cannot bond. Well, there's a bit of an exception to that, and this is the coordinate covalent bond. So, in this example here, carbon can move this electron, move it over to here, right? And we'll get two electrons on that side now, and no electrons on that side. Okay? And so what this then looks like is, let's see what we can do. Come on, there it is. It looks like this, right? Which now doesn't quite look right because there's a side with no electrons. However, what you're going to see is that this side is stable, it has its two. This side is stable, it has its two. This side is stable, it has its two. And oxygen is fully stable. Well, so it wants to make this molecule. So instead of having a one and one, oxygen will take these two electrons here, put them in the middle, and make a third bond to that side that has zero, because now you're sharing a pair between the two. And so it becomes carbon triple bonded with oxygen, and they each have a lone pair. Now, this isn't the ideal fashion to forming bonds, but it wants to form a bond, and this is a way to stabilize it. And so this is what's called a coordinate covalent bond. So when you're doing Lewis structures and you hit a wall, think to yourself, is there a way that on one of these things I can shift and create a coordinate covalent bond? All right. And it doesn't always happen like this with oxygen. Oxygen could shift its electrons around and have a blank side. So it's not always going to be one way or the other. It's any atom that has a pair could donate that pair in and form a bond. All right? And sometimes it's a little less than ideal, but it does happen. So let's take a look at an example and have you try one. Try out, let's get rid of this, but try out SO2. All right, pause it, try it out, and we're going to go over it in a second. Okay, hopefully you tried it out. And here we have SO2. And so we draw these things out. And now we have 3 atoms, all right? And so in this, we're going to assume sulfur ends up being in the middle because it's the first atom here. And so we're going to put an oxygen on this side. And an oxygen over here, it looks like. And so let's go ahead and try it out. Well, your first thought, of course, is going to be, well, let's make a single bond here and a single bond there, right? But now, sulfur, although sulfur's happy, neither of the oxygens are happy. And you cannot connect this. That makes the triangle, and you cannot have a triangle, okay? The angles to that bond are too tight. They will not form, all right? So you can't have triangles. So it's not going to bond here. So, well, you're stuck. You can't do anything, right? And we can't move anything around. There's no way to make that blank side that we did with the coordinate covalent. So what we have to do here is go back to the beginning and say, well, what on earth did we start to? Is there a different way to do it? Okay? And so we look at this, and let's get rid of those, and we say, well, how could we approach it differently? Well, instead of making a single bond and a single bond, I could do, well, a double bond between the oxygen, right? 1 oxygen, 1 sulfur. All right, now this oxygen's happy, and the sulfur's happy. So now let's think of our exception. Can we move the electrons around to have an empty side on sulfur or on oxygen? Well, clearly not sulfur. Sulfur's already full. It's happy. So what about this oxygen? Well, I take this one and I move it over, and I can reposition it right there. Get rid of this one, right? I now have my 6 electrons in the oxygen. And well, now sulfur can do its thing here. We can take these 2, put them in, and form a bond between a 2 and a 0. And when we redraw this, we have a sulfur double bond to that first oxygen, and then single bonded over to this coordinate covalent oxygen. And an important note is once this forms, the coordinate covalent bond does not operate any different. This is how it operates, okay? And so we get SO2, all right? And this is it, guys. Anytime you hit that wall, just think, is there a way that we could do a 2 and 0 instead of a 1 and 1? And that's all the coordinate covalent bond is.